Hello, and welcome to this tutorial for BioXTAS RAW. In this tutorial, we will learn how to use RAW to apply baseline corrections to size exclusion chromatography SAXS data. To do this tutorial, you need the RAW tutorial data, which is available on the RAW website. This tutorial also assumes that you know how to do basic operations for SEC-SAXS data, including things like loading data and selecting buffer regions. Sometimes SEC-SAXS data shows a baseline drift. This can be due either to instrumental changes such as beam drift or changes in the measured system such as capillary fouling. RAW provides the ability to correct for these forms of baseline drift using either a linear or integral baseline method. The linear baseline method is best for instrumental drifts, while the integral baseline method is best for capillary fouling. Both baseline methods apply a distinct correction for each Q value. So to do this tutorial, we're going to use the tutorial data in the sec data folder, and we're going to start by loading the xylanase data. You can see it loads up a series plot here. We're going to first set a buffer range in the LC series analysis panel. The auto range is fine for this tutorial. And once we've done the subtraction, once we've set the buffer range, you can see that there's still a very distinct upward drift to the baseline here for the data set. In this case, this is most likely coming from some kind of instrumental drift. This was probably a small change in the temperature of the system as the data was collected. So what we're going to do is we're going to apply a linear baseline correction in order to correct out this drift in the data set. It's important to note that in order to do the baseline correction here, you should only use buffer regions that are on one side or the other side of the data. You shouldn't use buffer regions on both sides. So to do the baseline correction, we're going to expand out the baseline correction area by clicking on the triangle. And then we're going to set the baseline correction to linear. What we see here is we get two regions on the plot corresponding to the start and end region, which suddenly become active. Now, if you look closely at this baseline drift, you see that it may be slightly leveling out here at the beginning. So what we're going to do is we're going to pick a region that's a little closer to the peak in order to set this initial baseline. We're going to pick a range there, and maybe to there. Now I'm going to expand out the end range to make it about equivalent length. I'm just going to round this off to a nice number by changing it to 480 to 530, so it's 50 frames. And then I'll just expand this end range out to be 50 frames as well. Like so. Once we've selected the start and end regions for the baseline, we click Set Baseline and Calculate. So what you see is that there's a warning that pops up here. It warns us that the linear fit is, the slope of the linear fit is not the same across all the different Q values. Typically speaking, just because of the noise level, this is not the case, but we still get the warning. So in this case, we're just going to click Continue. What you can see here is that now that's taken us to the baseline corrected tab, and you can see that the baseline here, this buffer is now nice and level and about 0. So in that case, the linear correction has more or less done what we hoped it would do. The upward drift that we previously saw is essentially gone. If we switch back to the subtracted plot, just by clicking here, you see there's now an orange line. This is showing us what the baseline that was applied is. And now we're going to switch back to the baseline corrected plot. From here, we'll just find a sample region as usual. I'm going to click on Auto to start. And then I can send that to the profiles plot. You can see it selected a narrow region. If we wanted to be a little bit more precise about it, we could zoom in and expand this out. And oh, sorry, I had the wrong button selected there. Zoom in, expand this out a little bit, and try to figure out what range we wanted, maybe a sample range that does something like that would be a little bit better. You can see that it's found an issue with some of the frames. This may just be the baseline correction isn't perfect. I happen to know this is more or less monodispersed, so I'm going to send that to plot anyways. If we want to see what this range would look like without the baseline correction, we can simply turn the baseline correction off. You can see the sample region gets propagated to the subtracted tab. Here I'm going to just send this to profiles plot again. Click continue. Then I'm going to turn the baseline correction back on so it gets saved. Set baseline and calculate again. And then click OK. Two things that you should know. First, if I reopen the window, it will set the baseline correction appropriately. We can open this tab, we can see the end ranges, we can see the line on the subtracted plot. Second, the profiles are now shown on this plot here. I'm going to hide that first one. And you can see that there is a distinct difference at low Q. I'll emphasize it by going to a log-log plot between the corrected, which is in orange, and the uncorrected in green. And if we do a Guinea fit, what we'll see is that the corrected dataset looks quite good, all the way down to the lowest Q, whereas the uncorrected dataset has a little bit of an uptick at the lowest Q that needs to be corrected. So in that case, the linear baseline correction has actually done exactly what we hoped it would. So next we're going to learn how to do an integral baseline correction. These are usually best for when you have some kind of, say, capillary fouling that's causing a constant change while the sample's eluting, but no change otherwise. So we're going to start by clearing all the data that's currently loaded in RAW. And then we're going to load the baseline HDF5 file here. This is actually a series that you worked with in a previous tutorial. It's the data in sec sample 1. So again, we're going to open up the LC series panel. We should verify that the buffer region looks correct. And then we're going to open the baseline correction section again. In this case, we're going to select integral. We can try to do an auto range for the integral section. That'll get us an initial start. Then we can zoom in near the base of this peak and correct it ourselves. So you can see the auto range is maybe a little bit close to the peak. It's still on the slope here. So I'm going to move this end range out a little bit. And I might move the start range out a little bit as well, just to be safe. I'm going to adjust the ranges here so that they're about the same length. 20 frames should be fine. As such. And then I'm going to set baseline and calculate. What you can see here is that previously the buffer on the right side of the peak was a little bit up, indicating that we had some accumulation of something on our sample cell while the peak was eluting. In this case, we've now got a buffer region on both sides is actually a little bit down due to the nature of the correction, but it's essentially level. The reason that this is actually down is that the integral baseline correction can overcorrect. It can't apply a negative correction, so it assumes that all the Q values must be increasing. For noisy Q values, particularly at higher Q, this isn't always the case, and so for those it applies zero correction when really maybe it wants to apply a negative correction, and you end up overcorrecting the sample by applying just this positive correction. If we go back to the subtracted plot, and we can zoom in on the baseline region here, you can see the orange line is the integral baseline that was applied, and you can see again it's overcorrecting. If we want to figure out what region of intensity it's overcorrecting in, for example, we can set different Q ranges. So we can pick a low Q range, lowest Q to 0.02. And you can see in that range the baseline is actually correcting pretty reasonably. Whereas if we pick a high Q range, like say 0.2, oh, I need to do the end range first. 0.27 is an end range, 0.2. That's actually maybe not quite properly corrected. If I bring this back down even further, 0.1 maybe, you can see that the overcorrection is definitely happening in the mid to high Q range. This is a sign that maybe for this data set there's just very little signal out there. We'd be better off truncating the Q range that we're using before applying the baseline correction, which is something that we could do if we wanted to. For now, we're just going to continue as we have before. I'm going to send this range to the profiles plot. I'm not going to bother selecting a new one. I'm going to turn off the integral baseline, send this range to the profiles plot. See what we get. I'm going to go back to total intensity just so the plot looks usual. I'm going to reset the baseline. One more thing before I leave this window. The integral baseline method was not initially developed for RAW, and so if you do use that method, you should cite the appropriate paper. If you click How to Cite, you can find it there. It's also available on the RAW website. So if I click OK now, I can go to the Profiles tab. I can see the two profiles, both corrected and uncorrected. You can see the main difference is happening out in mid to high Q. In this case, there was very little difference between the two profiles, and we probably didn't need the correction because that step in the buffer was so small. But this can be useful if you have more extreme changes across the peak. With that, that's the end of the tutorial. You should now know how to apply linear and integral baseline corrections to SEC-SAXS data in RAW.